when we analyze multi-degree of freedom systems like robots, we need to deal with multi-input and multi-output systems. Now, in a robot manipulator as opposed to in a mechanism, in a constrained mechanism, we have various links moving in space, or in a planar manipulator various links moving in one plane, and they can change their position and orientation as they move. Now, it is a very important thing in mechanics in general and kinematics in particular to be able to track a point in a moving frame. So, for example, we always talk of this problem that suppose there is a satellite or an aircraft which is in space, which is flying, and there is certain point which is moving with respect to the aircraft or with respect to the satellite, then the representation of motion of that point or particle is very easy in the aircraft frame or the satellite frame. But suppose I want to represent this same motion in the earth fixed frame, then it becomes a little complicated. Now, for this we use frame transformations. That simplifies the way we can relate these two this representation of vectors in a frame that might be moving, in a certain body which might be moving. So, we need to understand coordinate transformations in order to be able to represent a point or a particle or maybe another link which is mounted on a moving link. So, in this lecture we are going to start discussions on coordinate transformation, and we will see how these concepts are used in very easily analyzing robot manipulators. In these lectures we are going to restrict ourselves to the planar case. Once the planar case becomes clear, then going over to the spatial case or the 3-dimensional case becomes very simple. It is just a one step ahead. So, the overview of this lecture is that we are going to first start with the coordinate transformation. We are going to look at rotation matrix and its inversion, and we are going to interpret the rotation matrix so that we are able to understand the elements that construct the rotation matrix. Now, rigid body motion is tracked by certain coordinates. So, how do you track a body moving in space, a rigid body moving in space or on a plane? So, we have coordinates which are the position and orientation coordinates of the body. So, the position coordinates can be x, y, z, and the orientation coordinates can be rotations about the 3 axes. There are various ways of representing orientation. Here we are going to only restrict ourselves to planar orientation. So, in planar motion coordinates we have 2 position and 1 orientation. So, let me show you what I mean. So, in the plane, let us say at the xy plane, if I have a body so this dashed line is fixed to the body, then by tracking the xy of this point, let us say A on the body, and the orientation through this angle, let us say theta. So, this angle theta is the angle measured between the body fixed line and the x axis. So, we have these 3 coordinates x, y, theta. So, by keeping track of x, y and theta, I can uniquely locate the body in a plane. So, we have 2 position and 1 orientation coordinate. for planar motion. For spatial motions, we require 3 position coordinates and 3 orientation coordinates. Suppose I have a body in which a line is fixed, then I can locate coordinates of a certain point on the body and the orientation by looking at possibly the direction cosines, these angles that the line makes with the local x y z coordinate system, which is parallel to the blue coordinate system. So, by having these angles, let us say gamma x, gamma y, gamma z, I can fix the position of the body. So, x y z and gamma x, gamma y, gamma z, these will fix the position and orientation of the body in space. So, I require 6 coordinates for a body in space. Now, in order to track the location or motion of a point on a body which is in motion, maybe on the plane or in space. So, if I have a body which is moving in space, let us say, and there is something else which is also moving with respect to that body, I would like to find out the coordinates of that point in my earth fixed frame. So, this is what I want to find out. So, I want to track the location or motion of another point on the body. So, for that I require coordinate transformation. So, this coordinate transformation will take the coordinates of the point in the body fixed frame to the ground frame. So, that is the purpose of the coordinate transformation. Now, our plan for coordinate transformation I have listed out here. So, we will begin by looking at the rotational transformation, the planar case. Then we will look at the homogeneous coordinate transformation in the plane, and we will finally look at applications of the concept of coordinate transformation for analysis of robot open loop, open chain robots. So, we will start with discussing the rotational transformation. Let us consider a vector in the plane as I have shown you here. So, this p x is a vector. So, a p is a vector in the plane with coordinates p x and p y. So, normally we tend to represent this vector p as p x I cap plus p y j cap. Now, this p is a position vector, suppose it is a position vector of a point capital P. So, the vector p is a position vector of a point capital P. Let us consider a direction. Here I have represented as a cap, which is at an angle theta. I would like to find the projection of the vector p along a cap. So, I want to find out the projection of the vector p along the unit vector a cap. Now, you already know and we have also discussed the concept of projection. For example, if I want to project the vector p along x axis, then so if I want to project vector p along x axis, then I take a dot product with I cap and that gives me p x. Now, our problem is little more general. We have a unit vector a cap which is a direction at an angle theta with respect to the x axis. Therefore, I can very easily represent the unit vector a cap. So, cosine theta, I am writing c theta for cosine theta I cap plus sin theta, I will write s theta for sin theta times j cap. So, that is the unit vector a cap. So, therefore, projection of p along a is nothing but the dot product of p vector with a cap So, this is the p vector and a vector is and that gives us p x cosine theta plus p y sin theta. So, that is the dot product of p with a cap and this concept is what we are going to use for constructing the rotational transformation. So, let us see how we do that. So, this projection, so this distance is nothing but what I just now wrote out p x cosine theta plus p y sin theta. So, that is the projection and this is what we are going to use. So, now we are going to directly go into the problem of tracking a point on a rotating body. So, here I have shown you a body in position 1 which rotates and goes over to position 2. There is a point capital P on the body whose position vector is this vector small p. So, this point P goes over here upon rotation and the new vector is again represented here as p. So, small p vector represents the position of the point capital P. Here I have shown you the body in configuration 1. So, this is configuration 1 and I have also shown two frames. Here is one frame x 0 y 0 which we will fix. This is ground fixed. So, x 0 y 0 is ground fixed. The x 0 y 0 frame is ground fixed, whereas the frame x 1 y 1 is body fixed. So, the frame x 1 y 1 is body fixed and x 0 y 0 is ground fixed. What happens when we rotate the body? X 1 y 1 has rotated by this angle theta, as you can see. This was the initial position of point P, and now the new position of point P is here. Our objective is to locate the new point P in x 0 y 0. Here I have removed the original position of the body in configuration 1. So, we can only see the body in configuration 2, the body fixed frame x 1 y 1 and the ground fixed frame x 0 y 0. We can also see the new location of point capital P. So, this is the new location of point P. What I want to determine is this P x represented in frame 0 and P y represented in frame 0. In terms of P x represented in frame 1 and P y represented in frame 1. Therefore, I have these two representations of the vector P. Remember that it is the same vector P, which is the position vector of point P, capital P. In the ground fixed frame, the representation of the vector P is P x 0 I 0 cap plus P y 0 j 0 cap, where I 0 cap and j 0 cap are unit vectors along x 0 and y 0. And similarly, in frame 1, the representation of the same vector P is P x 1 I 1 cap plus P y 1 j 1 cap. Remember, this is the same vector P being represented in two different frames, nothing else. And we would like to find out the relation between this P x 0, P y 0 and P x 1, P y 1. This is what our objective is. Now, how do we go about doing this? I want to find out P x 0. So, how do I find out P x 0? P x 0 is nothing but the vector P dot I 0 cap, that is P x 0. Now, P has this representation in the new frame like this, and this dot I 0 cap. So, this becomes P x 1 I cap 1 dot I 1 cap dot I 0 cap plus P y 1 j 1 cap dot I 0 cap. So, this becomes P x 1. Now, what is I 1 cap dot I 0 cap? I 1 cap dot I 0 cap. Remember that I 1 cap is along x 1 and I 0 cap is along x 0. So, what is the dot product of two unit vectors which has angle theta between them? Is nothing but the cosine of the angle between the two vectors. So, this must be cosine theta plus p y 1. Now, j 1 cap dot I 0 cap. So, j 1 cap is nothing but a vector, a unit vector along y 1. Now, this unit vector j 1 cap I have drawn here dot I 0 cap. So, it must be cosine of the angle between I 0 cap and j 1 cap. Now, that angle is 90 plus theta, as you can see. You have 90 degree plus theta, that is the angle between I 0 cap and j 1 cap. So, this becomes cosine of the angle between the two, which is 90 degree plus theta. So, that becomes p x 1 cosine theta plus p y 1. Now, cosine of 90 plus theta is nothing but minus of sine theta. So, therefore, this becomes p x 1 cosine theta minus p y 1 sine theta. So, this is p x 0 in terms of, so this is p x 0 in terms of p x 1 and p y 1. So, we have related, we have one relation now, we have obtained one relation between p x 0, p x 1, p y 1 in terms of the rotation of the frames theta. Now, following this procedure, I can find out also p y 0. The procedure remains the same. So, which means I must have p y 0 as p dot j 0 cap, and then once again I use the representation in frame 1 . Carry out the dot product, write out the angles between the unit vectors, and I will get a second relation. So, that will turn out to be, I will have I 1 dot j 0, I 1 dot j 0, that is the angle. So, because both are unit vectors, so it is the cosine of the angle between I 1 and j 0. So, that will be cosine of 90 minus theta, which means this will be sine theta, and then I will have p y 1 times j 1 dot j 0. J 1 dot j 0 is the angle between j 1 and j 0, cosine of the angle between j 1 and j 0, and that is again theta. So, this will become cosine theta. This you can easily check. So, I have finally these relations. So, let me show these things formally. So, I have these relations. I have shown you how to obtain these relations. Now, I will assemble them. P x 0, P y 0, I will write as a column vector is equal to some matrix times P x 1, P y 1. Because I have these two relations, on the left we have P x 0, P y 0, and on the right we have P x 1, P y 1. So, I have written them as a matrix times p x 1 p y 1, and if you fill in the elements of this matrix from the individual relations, you will obtain this matrix. Therefore, I will write this in a compact form as P vector represented in frame 0 as the rotation matrix which takes me from frame 1 to frame 0 times P represented in frame 1. So, this is how we are going to represent these vectors and show in which frame they are represented in. So, this P 1 is represented in frame 1, P 0 is represented in frame 0, and they are related through the rotation matrix R from 1 to 0. So, we will always say it goes from 1 to 0. So, on the right hand side I will multiply by a vector represented in 1 in frame 1, and on the left I will get a vector represented in frame 0. So, this is the implication. So, just to show this thing formally, now we interpret this rotation matrix. If you look at column 1 of the rotation matrix, the column 1 you can very easily see is the representation of the vector x 1 or the axis x 1 in x 0 y 0. The column 1 is the unit vector along x 1 being represented in x 0 y 0. So, this unit vector being represented in x 0 y 0 is nothing but the first column of the rotation matrix. The second column is the representation of the unit vector along y 1 in x 0 y 0. So, I will write this is the representation of y 1 in x 0 y 0 frame. Now, if I interpret that this way, then it is very easy to construct the rotation matrix. I need not go through the steps that I have just now shown you. I can directly construct the rotation matrix. So, remember that the first column of the rotation matrix that takes me from 1 to 0 is nothing but the representation of the frames x 1 y 1 in x 0 y 0. So, the first column is representation of x 1 in x 0 y 0, the second column is the representation of y 1 in x 0 y 0. So, that will construct the rotation matrix 1 to 0. So, we can directly construct the rotation matrix. Let me do that. So, I say that I want to construct this rotation matrix from 1 to 0, that will take me from frame 1 to frame 0. Then I must represent the individual axis of the frame 1 in frame 0. So, frame 1, the first axis is x 1. So, let me represent x 1 in x 0 y 0. So, this will be cosine theta sin theta, and then the second column is the representation of y 1 in x 0 y 0. So, that is minus sin theta cosine theta. Now, when we invert the rotation matrix, is just the opposite thing that you do. You start with the vector representation in the two frames. Now, you do a dot product with I 1 cap to get P x in frame 1. So, that is the only difference. Now, if you proceed this way, similarly you will get P y 1, and therefore, finally, you can represent this vector is P in frame 1. So, therefore, this must be the rotation matrix that takes me from frame 0 to frame 1, and P that must be multiplied by the vector P in frame 0, and that is being represented here. You can very easily check that R from 0 to 1 is the transpose of R from 1 to 0. R from 0 to 1 is nothing but R from 1 to 0 transpose, and that expression you have here. So, therefore, once again a direct construction, let us look at a direct construction of R from 0 to 1. So, what do I now have to do? I have to represent the frame x 0 y 0 in x 1 y 1. So, frame the axis x 0, the first column will be axis x 0 in x 1 y 1. So, that you can easily check is cosine theta, this angle being theta. So, cosine theta and minus sine theta, that represents x 0 in x 1 y 1. The second column is representation of y 1, representation of y 0 in x. So, the second column is representation of y 0 in x 1 y 1. So, y 0 in x 1 y 1. Now, this being theta, so I must have sine theta and cosine theta. This is y 0 in x 1 y 1. So, that constructs the rotation matrix R from 0 to 1, and that you can check is the transpose of the matrix R from 1 to 0. So, therefore, here I have written out the direct and the inverse rotation matrices from frame 0 to 1 and 1 to 0. So, let me summarize what we have discussed in this lecture. We have looked at coordinate transformations, we have looked at the basis of coordinate transformation and why we need it. I have shown you how to construct the rotation matrix, and I have also given you the interpretation of the rotation matrix, and this interpretation helps us to directly write the rotation matrix by looking at the coordinate frame orientations, and we are going to use this rotation matrix in our subsequent discussions. I will close this lecture at this point.